So the title of this lecture might scare you a little bit. It's called Gas Equations. Okay? And we likely will do very little calculating in this class, but I at least want you to make you aware of these equations. And then if you understand how these equations work, you'll understand some of what's going on during exercise to your respiratory system. So here are our learning objectives, and like I just said, I haven't decided yet, this is a couple weeks before we get here, whether or not I'm actually going to have you calculate anything, but I'll definitely want you to be able to understand what's going on with these equations. So to start off, we need to have some definitions with the respiratory system. So we've got dead space, and that's any place in your lungs where gas exchange isn't occurring, okay? Meaning there's air there, but there's no blood flow there, okay? Or oxygen's not able to diffuse into blood vessels. And this can be broken up into two parts. Anatomical dead space, which is the part of your lung where just due to anatomy, gas exchange will never occur. This is a constant volume. Okay, so this is like air that's in your trachea. That's part of your respiratory system, but it's too thick, and we'll get into other reasons, but gas exchange can't occur there. And then we've got physiological dead space. And this is because there are parts inside your lung, there are alveoli inside your lung where there isn't really that much blood flow. And we'll get into that later as well. But because this isn't a constant thing, it can fluctuate due to pressures and other things. So this is, because it fluctuates, we call it physiological dead space. There's nothing wrong with the blood vessels. There's nothing wrong with the alveoli. The anatomy of them would allow for gas exchange, but at times, gas exchange just doesn't occur there. So then we've got Boyles Law, okay? And remember, Boyles Law is just saying if we have a specific or a constant temperature, that the product of pressure and volume is going to be constant, okay? And so that's what this little diagram is trying to show here. So how is this relevant to ventilation? Well, if you remember from what we talked about in our last lecture with the respiratory pump, that's an example of that, okay? The volume between we're in a closed system in our thoracic and abdominal cavities, but we can change the volume with the diaphragm, okay? And so when we change the pressure inside the thoracic cavity during inspiration, we lower it. That allows air to go into the lungs. We create that pressure gradient, flow down gradients, right? And so low pressure, air goes into your lungs. And then when you exhale, the reverse is true, and now air goes out. Now we're going to talk a little bit just for a second, because it kind of fits in with some of the equations that we're going to talk about, is something called the respiratory exchange ratio. And what we use this is as a way to estimate how much energy, and really not amount, but more the type of energy that's being used. Okay, each macronutrient, and specifically fats and carbs, require different amounts of oxygen to utilize, and they produce different amounts of carbon dioxide. And so what we end up doing with the RER is we've created a ratio that's the amount of carbon dioxide produced divided by the amount of oxygen used. So an example of this is if I produce 6 carbon dioxide molecules, but I use 6 oxygen molecules, then my RER is 1.0. Okay, so when we're burning fats or at rest, our RER is about 0.7. Okay, if we're only burning carbohydrates, our RER is 1.0. Now, it is possible for RER to exceed 1.0. We're not going to get into that right now, but we will later. So just remember it can be greater than 1. But generally speaking, it's 0.7 to 1.0. And the closer we are to 0.7, that means we're burning more fats. The closer it is to 1, that means we're burning more carbs. Now, we can't really measure how much pressure or how much oxygen's in a specific alveoli, or even in all the alveoli, so we can estimate that. But it's important to know that carbon dioxide and oxygen values or concentrations are not the same throughout the entire lung. Different areas of the lung are going to have different amounts of oxygen and carbon dioxide. Thankfully, though, we can estimate the pressure of each of these gases. And so we've got a couple equations that we're going to go through here. So the first one is alveolar oxygen. Now I want you to remember that we've got P big A and we've got P little a. So this big A here means alveolar. Okay, whereas this little a here means arterial. Okay, so alveolar oxygen, there's, 5 terms here. So we've got FiO2. Basically, that's the percentage of oxygen in the air that's being breathed in. Okay, so fraction of inspired oxygen. Okay, normally this is about, the actual value would be 0.2093. Okay. PB is barometric pressure. Normally at sea level, that's about 760. But if I go see my parents in Utah, it's probably closer to 600. Partial pressure of water, that will always be 47. Okay, and we'll basically what happens is we have to saturate the air that we breathe with water so that gas exchange can occur. PaO2, that's normally about 100. Okay. And then the respiratory exchange ratio that we just talked about a little while ago. Okay, and it can be anywhere from 0.7 to 1.0. And as I'm looking at this, there's an error. This is supposed to be CO2, not O2. Okay, so this value is normally 40. Okay, so if you did the math on this, our PaO2 would be pretty close to about 100. It's P big A, so alveolar oxygen. It's going to be pretty close to arterial oxygen, but it's not actually always the same. And we're going to talk about with the next lecture why that is. Okay, so if we walk through this though, here are the values that we'd put in. Respiratory exchange ratios between 0.7 and 0.8 at rest. That gives us a value of about 100. Now we've got, notice, just walk through this for a second. So what's going to happen at PaO2 if I change any of these numbers? If I increase FiO2, that's going to go up. If I increase barometric pressure, that number will go up. This one's constant, so it's not going to change. Okay. If I increase CO2, that's actually going to make this number go down. And if I increase RER, that will make this number go up. Okay, so you just have to use some math here. And the thing I tell people, if you want, just use simple math. Okay, if you're not sure, right? So we can just say that this whole thing here, it's not real, but we can just say it equals 1. Okay, and so then let's say that this is 1 divided by 1, right? Well, that would equal 0. Well, let's change this number to a 2. Okay, that would give us a -1. Okay, if we double our carbon dioxide, we're going to make P big A O2 go down. It shouldn't be surprising. If I've got more CO2, that means there's probably less oxygen in the air that I'm breathing. But if I flip it, this number will go. If I flip it, meaning if I do the same thing to RER, if I increase RER, my oxygen will go up. Okay, RER will go up like when I hyperventilate. And so if I hyperventilate, I'm bringing more air in. So we can do the same sort of thing with carbon dioxide. I don't believe there are any typos on this. So we can go alveolar CO2 equals VCO2. And so remember, VCO2 is the amount of carbon dioxide that I produce. And then we multiply that by a constant, and we divide by alveolar ventilation. Alveolar ventilation is different from minute ventilation. Okay, minute ventilation is just how much air you're bringing in and out of your lungs. Alveolar ventilation is how much of that air is actually undergoing gas exchange. So again, if I'm producing more, if I just change this number, that's going to cause my PaCO2 to go up. So that'll increase it. But if I increase my alveolar ventilation, just think hyperventilation, I'm actually getting rid of more CO2, so that number will go down. Since K is a constant, we won't mess with that. Okay, so we've just answered that question there. Whoops, don't know what I'm doing. If you keep constant the amount of CO2 you're producing, but you increase your alveolar ventilation, you're going to decrease your CO2. Okay, if we use typical textbook values, alveolar CO2 is about 41. Okay, Now, if I choose to calculate or have you guys calculate things, I would give you an equation sheet and I would give you the constants. Okay, so you wouldn't have to remember those. But I will let you know once we start this unit.